Hey guys, Miss Gosling here. In this video, we're going to talk about star lifetimes. By the end of the video, you'll be able to use the mass-luminosity relationship to determine the amount of time a star will stay on the main sequence. So let's go ahead and get started. So your understandings, applications, and skills, fun, no understandings, but your applications and skills, you do need to be able to apply the mass-luminosity relation to compare lifetimes on the main sequence relative to that of our sun. And one thing I want to point out is that we're only looking at comparing lifetimes relative to our sun, so you should not be expected to compare lifetimes of two other random stars. So what I want you to do is take a moment and look at my three stars. One star is red, so it has a low luminosity. One star is yellow, so it has a medium luminosity. And the last star is blue and has, therefore, a high luminosity. What I want you to think about is which star will burn through its hydrogen reserves fastest. Go ahead and make a prediction, and then we'll talk about it. So the star that will burn through its hydrogen reserves fastest is the blue star. And the reason for that is that this star is producing significantly more power. Therefore, it is producing more energy per second, and that energy is coming from the collisions between hydrogens. So what that means is that it is having more collisions per second, so more fusion reactions per second. And as a result, it's going to burn through its hydrogen reserves much more quickly than my other two stars. So the actual relationship between mass and lifetime on the main sequence is that lifetime is proportional to mass to the negative 2.5. Now, you may ask yourself, wait, Miss Gosling, in the last slide you were talking about how the more luminous a star was, the shorter time it'll spend on the main sequence, but now you're switching from luminosity to mass? What's going on? We have not yet talked about the relationship between mass and luminosity for main sequence stars, but in our next topic we will. So for now, I am going to just ask y'all to accept that mass and luminosity do have a relationship, and that is why we are able to use mass here instead of talking about luminosity. And one note I want to give you is that this equation is not in the data booklet. If you want to be able to use it, you do just need to memorize it. So let's go ahead and do an example. Proxima Centauri is a main sequence star with a mass of 0.12 solar masses. So that's 0.12 times the mass of the sun. And we are being asked to estimate the lifetime for Proxima Centauri divided by the lifetime of the sun. So let's go ahead and look at that. So I know that lifetime is proportional to mass to the negative 2.5. So if I want to do the lifetime of Proxima Centauri divided by the lifetime of the sun, what I'm going to do is I'm going to go ahead and just slightly change this proportion. So I know that mass to the negative 2.5 is the same thing as 1 over mass to the 2.5. So what that means is that if I want to look at the life of Proxima Centauri, PS, divided by the life of the sun, that's going to equal the mass of Proxima Centauri to the 2.5 divided by the mass of the sun to the 2.5. And the reason the mass of the sun and the mass of Proxima Centauri are on opposite sides of my fraction as the lifetimes are is because of that little negative sign in the exponent for that original proportion that we looked at. So let's go ahead and simplify. So I know that the mass of the sun is just the mass of the sun. I'm going to go ahead and take the 2.5 out of my fraction. And I know the mass of Proxima Centauri is 0.12 times the mass of the sun. Therefore, that ratio of lifetime is going to be equal to 1 over 0.12 to the 2.5. So there are a few different ways I could solve this. For me, the easiest thing is to just stick this in my calculator and do 1 divided by 0.12, hit enter, and then raise that answer to the 2.5th power. And when I do that, I get that the lifetime on the main sequence of Proxima Centauri divided by the lifetime of the sun, that ratio is approximately 200. So what that means is that Proxima Centauri will spend about 200 times as long on the main sequence as the sun will, which is kind of interesting, right? So let's go ahead and talk takeaways. First of all, the more massive and therefore more luminous a star, the less time it will spend on the main sequence. And we know that star lifetime is proportional to mass to the negative 2.5 for main sequence stars. Now, one thing I do want to point out, that statement that we're talking about main sequence stars is really important. This is only relevant for my younger stars that are still converting hydrogen to helium. Once a star becomes a red giant or a white dwarf or a neutron star or a black hole, the relationship between lifetime and mass is no longer relevant. I also want to mention that, or just remind everybody that this equation is telling me the time the star will spend on the main sequence, not the total time that it will exist in general. So this is telling me how long from its birth until the time between its beginnings as a star, so when it turns from a protostar into a star, it's the time from that moment until the moment it becomes a red giant. So there you have it, guys. We have now learned all about the lifetime of stars. It is now your turn to go out and try solving some problems on your own. Best of luck and happy solving.